Welcome to this morning session. So our first speaker is Thiago Fassarella from the UFF Niterói. And he talk about singular fibers of the Hitchin map.
Thank you, Daniel, for the introduction. So I have had the privilege and the opportunity to work with Frank in the past 10 years. I think. So 10 years. Yes. So thank you, Frank, for sharing ideas and, of course, the best part, your friendship. Okay, so today I'm going to talk about some moduli spaces of logarithmic connections and Higgs bundles and the Hitchin vibration. So C is going to be a complex curve, I mean a Riemann surface of genus G with a set of points which I will use as poles for connections and for Higgs bundles. Okay. So using this data, we can construct some moduli space. For instance, you know the moduli, the representation variety, which is formed by homomorphisms by representations of the fundamental group. This is a topological object. I mean, it depends only on the topology of the base curve. And there are also the moduli space of logarithmic connections on C with poles on D, and the moduli space of Higgs bundles that depend on the complex structure of the punctuatory curve. They are algebra geometric incarnations of the representation variety via the Riemann-Hilbert correspondence, as it was explained by Professor Saito, and the non-abelian Had theory. So let me give you some motivations to study such moduli space. The moduli space of connections is the space of initial conditions for isomodromic deformations. And the Higgs bundles form an algebraically completely integrable system. So there's a vibration, which is the Hitchin vibration, whose fibers are Jacobian varieties of spectral curves. So the picture is this. So there's a moduli space of Higgs bundles, which contains the moduli space of bundles by taking the Higgs field to be 0. And there's a map from an affine space that I will define soon, which takes a Higgs field and associates, for instance, its determinant. And the generic fiber of this map is an abelian variety. So if we take the projection for getting the Higgs field, this gives a map to the moduli space of bundles, which is a ramified covering from an abelian variety to the moduli space of bundles, of vector bundles. So this is a sort of Abelianization of the moduli space of bundles. Maybe it's one of the main motivations to study moduli space of Higgs bundles. But there are few examples in the literature. For compact curves, the first interesting case appears in genus 2, and corresponding moduli spaces have dimension 6, or 6-dimensional varieties. So in this talk, I want to look at some explicit examples. Okay. Now, for the moduli space of connections, we fix a weight vector, a vector of complex numbers, and
so the rank is fixed. What's the rank?
I'm going to fix all the notation. It's just a rough introduction. But the rank is fixed, yes. In my case, I will take rank 2 all the time. So we fix the eigenvalues for connections, then there is a moduli space of SL2 logarithmic connection, so rank 2, and trivial and vanishing trace. And vector bundles have trivial determinant line bundle. The moduli space has dimension 2 times 3g minus 3 plus n. And if you look at 3 points on P1, then this moduli space is a point which corresponds to the Gauss hypergeometric equation with poles, Dulce poles. And the parameter of the Gauss hypergeometric equation is determined by eigenvalues of the connections. If you look at n greater than 3, then it is a symplectic variety of dimension 2 times n minus 3. So here I'm fixing genus 0. That can be viewed as the space of initial conditions of isomodromic, classical isomodromic deformations. The case n equals 4 is the corresponds to the Painlevé equation by doing isomodromic deformation. And for greater than 4, it is called a Garnier system. So let's consider some. As I said, I want to look at some specific examples in constructions. So let me just mention some results. If you look at 4 points on P1, so the genus is 0, and we fix generic eigenvalues in order to avoid reducible connections, then this moduli space with this fixed data is the blowing up of a Heisenberg surface F2 at 80 points minus a sweet-spot visor. And it is analytically equivalent via Riemann-Hilbert correspondence to a cubic surface, but not algebraically equivalent. For arbitrary number of points, Frank and Saito, they showed that there is a map which is ban times app. This is the map that forgets the connection, and this is the map that takes the apparent singularities. In these maps gives a birational map between the moduli space of connections and the product of Pn minus 3. Actually, they show that there's an open subset of the moduli space of connections that embeds in the product minus the diagonal. So it's a beautiful and simple construction.
Birational with image or birational
Is one-to-one to the complement. There's an open subset that is one-to-one to the complement of the incidence variety, right? Okay. For high genus, there are some cases that can be reduced to the genus 0 case. So, I mean, we fix the projective line with some points, and then we can take a connection on P1 and we lift to the elliptic curve, then this gives the connection on an elliptic curve. So we have a map from the moduli space of connections on P1 to the moduli space of connections on the elliptic curve, either with one poles, with two poles, with the same eigenvalue, or holomorphic connections on a curve of genus 2. So this map is surjective. Then you can take advantage of this construction to study the moduli space of connections on such hyper elliptic curves. So Frank, in 2006, studied the first case, and with Loray and Ramirez and Valente Ramirez, they studied the intermediate case, and with Vitória, Frank with Vitória EU, studied the case of the curve of genus 2 in 2009. There are some results that cannot be reduced to genus 0 case. For instance, you take the elliptic curve with 2 points, but with different eigenvalues in each pole. If you take a general connection in this moduli space, it cannot be obtained by P1. So this is different from the other case. So with Frank, we studied this case, and then soon after with Alain Muniz, we extended this description to the arbitrary number of points. And there is also a paper by Matsumoto for arbitrary genus. Okay. So this was a quick recap on some results for some explicit constructions and descriptions for moduli space of connections. Then and for the rest of the talk, I want to discuss some similar ideas for Higgs bundles. Okay. So what about the Higgs bundles? The case we are interested in is the projective line with 5 points. So I take the P1. With 0, 1, let's say lambda, infinite, and t. So I take 5 points on P1 and 2 points on the elliptic curve. The elliptic cover, which is a 2-by-1 map that ramifies over 4 points. Then we look at the moduli space of Higgs bundles. With rank 2 Higgs bundles on C with 5 points, in the moduli space of Higgs bundles with 2 points, and the construction is as follows. We start with the Higgs with a Higgs field over P1 with these 5 parabolic I mean logarithmic singularities. Then we lift to the elliptic curve, but as we will see that the singularities over, since this map is branched, the singularities are apparent, which means that we can perform an elementary transformation in order to eliminate singularity over the set of Weissner's points. Then what we get at the end of the day is a Higgs field with 2 logarithmic singularities. So this gives a map from moduli space which have dimension 4 that preserves the Hitchin fibration in both sides. And the goal of the talk is to address the following questions. Is this modular map surjective? And what about the ramification locks and singularities of the moduli space? Can we relate the ramification locks and singularities of the moduli space with the Hitchin fibration? So the first, we use the results of these works with Frank. In the first case, we studied the variation of the Hitchin fibration under a ramified covering between curves. And in the second paper, we studied the fibers of the Hitchin map, but the singular fibers of the Hitchin map in the P1 side, because we know that the general fiber is an abelian variety, but in general, the singular fiber are difficult to deal with. But it's difficult, at least for me. So we study the singular fiber. We have a description for the singular fibers. And then now we use the modular map in order to give a description of the singular fibers on the elliptic side. Okay, so let's move to Higgs bundles. I'm afraid that now the talk will be a little bit technical. As before, we fix the curve and the set of polar singularities, the set of n points. Then what is a Higgs bundle? The Higgs bundle consists of a pair given by a rank 2 vector bundle, so everything is in rank 2 here. And the Higgs field is a homomorphism of E of the vector bundle with coefficients on the sheaf of 1 forms with simple poles on D. I assume that the trace is vanishing, and the residual matrix of the Higgs field on each pole is nilpotent for all points. Those points I will call the parabolic points. So there is a parabolic structure which is for each point. So you fix the vector bundle E, for instance. And the picture is the projectivization of E. And for each parabolic point, we have a projectivization of the fiber on Ti. And the parabolic structure is a line subbundle on the fiber over each parabolic point. And in order to give to define in the modular space, we need a notion of stability. And this notion depends on weight vectors, on a sequence of weight vectors, which gives the notion of stability for the modular space. So for each line bundle L, we define the degree of stability as follows. It's the degree of E minus 2 times the degree of L. So the first part of this is, for instance, take a line sum bundle, so this gives a section. The degree of E minus 2 times the degree of L is just the self-intersection of this section. And you consider the plus or minus mu I, depending if the parabolic point lies or not in the line inside the subbundle, the line subbundle. So this notion of stability, with this notion, we say that this Higgs bundle, so the Higgs bundle is stable if the stability degree is greater than 0 for every line sub-invariant line subbundle of phi. And it will be semi-stable if it's non-negative, and unstable if there exists a line subbundle such that the stability degree is negative. So just to have an example, take, for instance, in this case, we take the elliptic curve with 2 points, T1 and T2. So C is elliptic. And consider a line bundle of degree 0. Degree 0 on C, and fix a holomorphic one form on the elliptic curve, which is determined up to multiplication by a constant. So fix a holomorphic form. Then we define the Higgs field as a diagonal Higgs field, just like this. So this gives a map from L plus L minus 1 to L plus L minus 1 times to the sheaf of one forms, which is, indeed it is a holomorphic, so the residual matrix of the map is identically 0. Then we can choose the parabolic direction. You can choose the parabolic direction as you wish, because the parabolic direction must be contained on the kernel of the residual part of the Higgs field. But the Higgs field is holomorphic, so there is no residual part. The residual part is vanishing. Okay? So you can choose the parabolic direction as you want. Then for this Higgs field, so this one, because the parabolic directions lie on the subbundle, we fix the weight vector a half and a half. Then this one is unstable because the self-intersection of this section is 0. So this one is unstable. This is a strictly semi-stable. And this one is stable. Okay. Then there's an important result which says that the corresponding moduli space of Higgs bundles is of mu semi-stable SL2 Higgs bundles is an irreducible and quasi-projective array, and which is smooth on the stable locus, okay, the moduli. And an important remark is that it contains the moduli space of semi-stable bundles by taking the Higgs field to be 0. Now, one of the main ingredients I want to use is the elementary transformation, just like Roberto explained yesterday. So what I mean by an elementary transformation, we fix the parabolic bundle, and the projectivization is a Rayleigh surface. So the parabolic bundle is a Rayleigh surface with some fixed directions on fibers. Then we can perform a blowing up at those points. So you see there was a zero self-intersection curve, which is now a -1 curve after blowing up. Then we can blow down this curve in order to obtain a new Rayleigh surface. And this construction gives a modular map from Rayleigh surface with parabolic directions to Rayleigh surface with parabolic directions. And from the point of view of vector bundles, this new, the transform Rayleigh surface is the projectivization of a rank 2 vector bundle. And this vector bundle is just the subsheaf of E defined by sections passing through the parabolic direction. So this is still a rank 2 vector bundle. then we have a map between moduli spaces of parabolic vector bundles. And now let's look at locally what happens. So assume that the parabolic direction is given by E1, this, then E prime, the transformed vector bundle, is the subsheaf of E defined by sections passing through E1. So this is just is something like this section. So this is still a vector bundle of rank 2. And there is another direction which is determined by E2 for the transformer vector bundle. But we want to continue with this notion of stability of the vector bundle. We want, if a vector bundle was stable, we want that the transformed vector bundle after elementary transformation remains stable. So we need to we need to change the weight vector using this. A simple but important remark is the following. If you consider the weight vector as a half, like this case in this example, then this change does not change the weight vector. It is the same. So if you fix, in your moduli space, fix the weight vector as a half in all the coordinates. So the elementary transformation gives a symmetry of moduli space. It gives automorphism for this moduli space, because the weight vector does not change. And I will need this definition. Just before this, locally the picture is quite simple. The Higgs field is just a matrix of one forms with poles with simple poles on parabolic points. So it looks like this. But the matrix is the residual matrix is nilpotent with respect to the parabolic direction. So it has this local form. And the elementary transformation is really simple. Locally, it looks like this. Then I will say that the Higgs field is apparent if it is holomorphic after elementary transformation. So let's go back to our main set. We go from moduli space of P1 with 5 points to the moduli space on the elliptic curve with 2 points. So we might assume that C has this equation on P2. And the 2x1 map, the elliptic cover, is just the projection to the first coordinate. Just to fix some notation, T is going to be the divisor of 5 points. So let me write this here. On P1, and D is going to be the divisor on C. And we do this construction. We take a Higgs field on P1 with 5 parabolic points, with 5 logarithmic singularities. We lift this Higgs field to the elliptic curve, but the singularities over Weierstrass points, over ramification points of the 2x1 cover are apparent. We can check that singularities are apparent. Then we perform an elementary transformation over the set of Weierstrass points. And then we get a holomorphic Higgs field. So this gives a map between moduli space. This is the map that I call pi. P1, thank you. P1. So this is the result we are interested is we fix the weight vector as a half because elementary transformations are symmetry as automorphism of the modular space. So we fix this weight vector in both sides. Then the map, the modular map is surjective. This implies that any Higgs field on C can be obtained from P1. And we studied its ramification locus, and in particular, the branch locus of the modular map and singularities of the modular space on the elliptic side. There's a Galois involution. There's an involution of the covering. So let me fix lambda for those points. So there is a Galois involution, the involution of the paper, of the map, which is given by an elementary transformation over this locus. So the map is 2 by 1, and this is the deck transformation of this map. Now, the Hitchin vibration is a map that goes from Higgs field to an affine space of quadratic differentials. It takes a Higgs field and associates its determinant. So it goes from the modular space to an affine space. In our case, our specific case, the Hitchin map is just the determinant. So it goes to an affine space, which is twisted by 2. To an affine space, which is H0 of, here's P1, here's the, maybe this, here's the elliptic curve, and the affine space has a dimension 2, so it is a C2, actually. And the map, which is the elliptic curve, gives a map between the basis of quadratic differentials, which turns out to be an isomorphism. So there's an isomorphism between bases of quadratic differentials. Then we take a Higgs field, let's say phi, a Higgs bundle, a vector bundle, a Higgs field, and a parabolic direction. Then we send to a quadratic differential, Q. So I'm going to consider a curve, which is called the spectral curve, which is just the curve of eigenvalues in modular space. Then we do a easy computation with the Higgs field, and we see that the spectral curve is determined by this equation. So it is a curve of genus 2 ramifying over 6 points on P1. In general, that yes. And there's an extra point, which I call S. So the spectral curve is a curve of genus 2, ramified over the 6 points on P1. But the extra point can move on P1. Then each time the extra point coincides with one of the previous parabolic points, which are fixed, then we get a nodal spectral curve, an irreducible but nodal spectral curve. So the picture for spectral curves is as follows. So the types of spectral curves. Either it is smooth, but it can be singular. So let's assume, for instance, that S equals 0. Then we get a nodal curve like this, with order 5 over 1 lambda infinity and t. So this is a curve of arithmetic genus 2, but it is an elliptic curve with a node. And I will separate the two cases because the elementary transformation, which plays an important role, does not touch the parameter t. So if the spectral curve is nodal on t, like this, there's so much. So this nodal and nodal. Here S belongs to 0, 1, lambda, or infinity. And here S is equal to t. So this is the picture for the P1 side. So these are all the types of elliptic curves that can appear on the P1 side. For any Higgs field, there's a case which is missing, which is the zero, the elliptic curve z square equals 0, which gives the nilpotent point. But I forgot this case I'm forgetting this case for instance, but over the elliptic curve, and we will get 3 types of spectral curves. Then the first is a curve of genus 3 over is a 2-by-1 map over étale map or ramified map over C with 4 ramification points that gives a curve of genus 3. Or in this case, for each one of these cases, we get a nodal curve if S1 is S2, which is one of the Weierstrass points. Or finally, for this case, the curve will be nodal at T1 and T2. So a nodal curve at T1 and T2, we can see it's a local computation that actually it will be reduced curve like this. So this spectral curve will be reduced with two components which are isomorphic to one. This is a curve of genus 2 with a node like this. And the general spectral curve is a curve of genus 3. So each time S, the point, the parameter S, coincides with one of the 5 parabolic points, then we have a line in the basis, in the Hitchin basis. This, so we have 5 lines. Meaning that S is equal 0, 1, infinity, t, and so on. Because actually the parameter space of quadratic differential is determined by Q. And Q is the parameter that determines the elliptic curve. Oh, sorry. How can I go back? Yes. So Q determines the elliptic curve. And if you take a scalar up to scalar multiplication, this is the same. The line determined by Q determine actually the same spectral curve. So this set of lines is a set of singular spectral curves. So there are 5 cases. And there is also the same on the elliptic side. There is a set of singular spectral curves. And this isomorphism will send each line to the one side, to each line to the other side. Okay. Now, this diagram, I think I will skip the diagram. This was just to explain that the spectral curve of genus 3 is actually hyperelliptic. Okay. Now, I want to sort of Abelianization in the following sense. We fix a spectral curve. Say like this. We start with the Higgs field, phi. Then we look at the determinant, which is Q. Then we look at the curve of eigenvalues for this Higgs field. So this is a curve, 2-by-1 curve over our base curve. But the Higgs field is, we can see as a homomorphism of the vector bundle. So inside the vector bundle, let's say this is the projectivization of E. Inside the vector bundle, we can look at the curve of eigenvectors. Not only the curve of eigenvalues, but the curve of eigenvectors. So there is a curve of eigenvectors of phi of the Higgs field. And for each eigendirection, for each eigenvalue, we can attach to this the corresponding eigenvector. So this gives a fiber like this. In this construction, for each phi, we associate a line bundle on the spectral curve. Okay. So this is which is called the Hitchin correspondence between Higgs fields, Higgs pairs, and line bundles on the spectral curves. Now, for any Higgs field that have the same determinant, Q, so they have the same spectral curve. Then we can look at pairs of Higgs fields have the same determinant, and in order to give a correspondence between Higgs bundles, Higgs fields, and line bundles on the spectral curve. But if the spectral curve is singular, like this case, where the spectral curve was nodal, then we can check that we have not only one eigendirection associated to this point, but we have two eigendirections associated to this point. So for those singular points, we do not consider line bundles, but instead of consider line bundles, we consider rank torsion-free sheaves of rank 1, which means that at this point, we do not have just one eigendirection, but we have two eigendirections to this point. So this sheaf is generically, it has a rank 1, but there is a fiber of rank 2. Here. So this correspondence is what is called BNR, because of Bovid, Narasimha, Ramana, that gives this correspondence between Higgs bundles and torsion-free rank 1 sheaves on the spectral curve. So there is a variety which parameterizes classes, equivalence classes of torsion-free rank 1 sheaves, which is the compactified Jacobian. Now, finally, our modular map that goes from Higgs bundles on P1 to Higgs bundles on P2 preserves the Hitchin fibration. So using this correspondence, the Hitchin and BNR correspondence, the general fiber of the Hitchin map, the generic fiber of the Hitchin map is an abelian variety, like this one, which is isomorphic to the Jacobian of a curve of genus 2. And on the elliptic side, the general fiber of this map, because we are considering trivial determinant line bundles, so the general fiber of this map is the prime variety, which is also a Jacobian, which is also an abelian variety over a curve of genus 3. So moduli space have dimension 4. The basis has dimension 2. The fiber of this map has dimension, is two-dimensional. And this is a two-dimensional variety, and the map goes from a two-dimensional variety to a two-dimensional variety. This is the modular map. And there is a map between spectral curves that I didn't explain on that diagram, but there is a map, see, between spectral curves. And this map, this modular map that we have constructed is just the pullback of between the spectral curve. So this is, we can see that this is a 2x1 map, and this is also a 2x1 map between abelian varieties, which is determined by, essentially by the pullback of PC up to a translation. And now, which is missing is what happens for each singular spectral curve. It's the case which is much more difficult. So the time that I have, maybe 1 minute. I don't know. Yes? 2 minutes, 2 minutes. Let's negotiate. So for the time that I have, the singular fiber of the Hitchin map in these blue lines, when Q is different from the line, the spectral curve nodal over T, we show that the fiber has two components, like this. This is actually a resolution of the compactified Jacobian variety. And the elementary transformation, which is an evolution of the modular space, it will switch the two components. That's like this. And the image of this component by the modular map is a compactified Pring variety, like this, on the elliptic side. And finally, for the last case, when the spectral curve is nodal over T, then the spectral curve on the elliptic side is reduced, like this. So if it is nodal at T, then the involution of the modular space does not switch the two irreducible components of the Hitchin vibration. So it's something like it has two irreducible components, but the involution acts like this. So the image of the modular map will be two components. The other side. So that's the picture for the modular map. Finally, there's a fiber which is maybe the most difficult fiber, which is the nilpotent cone. Then we studied the nilpotent cone, and we found 17 components over P1 and 9 components over the elliptic curve. So there are 17 components. That goes to 9 components. One component is the modular space of semi-stable bundles. And there are 16 components which are permuted between them by the elementary transformation that goes to 80 components on the elliptic side. So once we have studied the modular map, the restriction to each fibration, it is surjective at the level of fibers. Then the modular map, the complete picture is surjective. And we can study the locus, the ramification, and the branch locus of this map. So this was the picture for the nilpotent cone. And finally, this is the result that I was telling you. So the map is surjective, 2x1 branched coverage, ramified over the locus of holomorphic Higgs fields. And this is the description that I did for each fiber of the Hitchin map. And to finish, a curiosity is that the singular locus of the Higgs, of the modular space over the elliptic curve, coincides with singular points along singular fibers of the Hitchin map. Okay, so thank you, joyeux anniversaire, Franck, et merci beaucoup pour tout.